So we were waiting for you. Okay, let's continue with the second. Is the second talk now, right?
Yes, yes, it's second.
Of Leandro's course on
last passage percolation. Okay. Okay, thank you.
Too much polymers, too much.
Yeah. I prefer to call them geodesics.
Yeah.
Okay, so let me remind what we have seen since now. So I'm very happy that Eric, did all the hard work in these 2 lectures, and now I can also use. So you are kind of used to all the objects that we are going to see here again. But let's just remind you the model. So we are dealing with last passage percolation. And differently from what Eric was telling you, we are working on last passage percolation on Z2. So we have the lattice, and on each point, on each side, we have a random variable that represents the passage time or energy, everything you want. And so it's in Z2. And so we have a collection of random variables that are distributed according to exponential of parameter 1. And this is the environment. And we were studying this object, which is the last passage time. So we have 2 types of last passage times. The point-to-point, which is denoted by L from X to Y. And this is defined as the maximum over all possible paths, upright paths. So this is the set of upright paths from X to Y. Obviously, I'm always taking, I'm always considering X smaller or equal to Y, coordinate-wise. Okay, so here in Z2. So this is the maximum over all paths from X to Y of the sum along the path of the weights. And then we also have the curve to point, which is I think I use a different notation. So I denote it like L from X to Y, and the curve to point I denote L from eta to Y. So eta is a downright path. So in this picture, eta is represented by this black path here. Okay, I'm assuming that it passed through the dual of 0. Okay, it's a path that lives in the dual lattice. And so the definition is very similar. So I'm taking the maximum, but now over all paths, upright paths from eta to Y of the same object, of the sum of Z from P of exponential Z. Okay? Each side, on each side of Z2.
And so that's Cij, for example, and then you are exponential e to the Cij.
No. This just means that this is a random variable. With distribution given by exponential. Of parameter 1, lambda equals 1. Okay, I just write just to call the attention that here I have exponential random variables. Okay, and I maximize over this environment.
And this L eta of Y, you could also maximize over all x in
Take Lx of 1.
Yes, yes, you can write it as also as, you can also maximize over all x in eta. Of course, x has to be smaller than y of Lx, L from x to y. That's the relation between the point to point and the curve to point. Less passage time. Okay? So how do we construct this type of object, the competition interface? So I will draw the path here. So suppose this is my path. So this is 0 dual. So this is my eta. This is my initial curve. Okay? And I will represent this curve as a union of two pieces. Okay? So this is the first piece, is what I call eta minus. And this is the other piece, what I will call eta plus. Okay? So eta plus is eta from 0 on, and eta minus is eta till 0. Okay? So I split this path in two parts. And so there are some important parameters related to this initial curve. So I will assume that this path here has an asymptotic direction, which is given by a parameter p plus. So p plus will represent the frequency of times that you go down. So 1 minus p plus represents the frequency of times that you go right. Okay? And you also have the p minus with respect to eta plus. So the asymptotic direction here is minus p plus divided by 1 minus p plus. Okay? So p plus is a number between 0 and 1. And I have the asymptotic direction here, which is minus p minus 1 minus p minus. Okay? And so what we are going to do here, so we are going to do the following. So remember that we have, for each realization, almost surely I will have a geodesic, which means that I will have an upright path from eta to y, which attains the maximum. Okay, so I have this, the geodesic, which is the path, we'll call it pi eta to y, is the path that attains the maximum. Okay? And then I will do the following. So for each point y that belongs, to this part of Z2, I will see the geodesic from eta to y. And if the starting point of the geodesic belongs to eta plus, then I will paint, I will put a color in this geodesic, and the color will be blue. And if the starting point of the geodesic belongs to eta minus, I will color it red. Okay? So this is the way we construct this figure here. And the competition interface is exactly this path here, which separates the blue and the red region.
Is it essential that there's a corner in 0 or not for this definition?
And somehow it's essential that, I want to, first you need to define where, you have the division between eta plus and eta minus, okay? And I also want that the competition interface start at 0, at the dual of 0. Then it's somehow it's just a matter of fix the starting point of the competition interface. Otherwise, it could be also random, the place, and if eta is random, so okay.
Does the black curve somehow satisfies the point-to-point geodesic problem or not?
This one here,
Yeah.
not really. It will satisfy a recurrence relation also, because the geodesics, we will see this later. There is a way, if you know all the last passage times, there's an algorithm to recover the geodesic, which is just what we call the argmax algorithm. So you start at some point, and then you look which one is the maximum value, and then you choose the one who I think is the maximum, and then you follow this. And if you keep doing this, then you are constructing exactly the geodesic between the point y and eta. Okay? So the competition interface will follow an argmin type of procedure, of algorithm. Because the geodesic will start here, and then it will look, I'll go up or I'll go right. And we will see, okay, I will go right if this point here is red. Okay? Now, if this point is blue, then I would go up. And this point to be red means that the passage times from here to here is bigger than the passage times from here to there. So I will follow the minimum here, because this is the minimum, so I go right. Okay. And then I keep doing this. So there is a relay, there is also an algorithm that somehow resembles the algorithm to get geodesics, but in a very special case, then you have some sort of reversibility of the last passage, which will tell you somehow that competition interface and geodesics, they have some similarities. Somehow they have the same distribution, but then you have to reverse the whole process. But this is in equilibrium. We will see this, I think, in the next class. But in general, no, there's no link at all. Okay, just in one very special case, we can have this relation between geodesics and competition interfaces. Okay. Okay, so where was it? So I would just want to write down some other stuff here, because it's also be important for us. So I will always be assuming that we are in the Rarefaction regime, which means that if I define mu plus as the square of this guy here, then it's smaller than mu minus, which is the square of that guy. Okay.
That's the same as saying rho minus small rho plus.
Yes. Yes.
BP.
Yeah. Yeah. In that case, means that you have less particles to the. So if you think that P plus is some sort of density of particles, because this is connected to the dataset, so it means that P plus is smaller than P minus. Okay? So you should think like, if P plus is allowed to be 0, and P minus is allowed to be 1. Okay, P minus be 1 means that you have like this, and P plus 0 you have like that. Okay? Yeah. Okay. Yeah, so the theorem that we want to prove is the following. So before I state the theorem, so I will define these two random walks. Okay, so these random walks, they are associated to the initial profile eta. And we have seen this before when we compute the invariant measure for the fluid system. We have seen that, the exponentials with some parameter, 1 minus rho, and rho correspond to the direction that you go with the Busemann function. So it will appear again because what we were going to do is we were going to relate this competition interface to the Boltzmann function, and then use the theorem that we have seen about the Boltzmann functions. We will actually be able to prove some convergence of the competition interface, and also to compute somehow what is the law of the asymptotic direction of the competition interface. And this random walk will be related to the asymptotic direction of the competition, to the law of the asymptotic direction of the competition interface. So let me say a few words about this random walk. So what we are going to do here is, so we will have this zeta k, eta will be associated to eta plus. So this S whole n plus eta. So I will sum along eta plus, okay, the increments which will be signed exponential random variables. And the sign and the parameter rho will depend on the step of the path. Okay? So every time I go to the right, so if I do like this, then I will have an minus exponential rho. I will sum a minus exponential rho. And if I go down, I will sum an exponential with 1 minus rho. So given eta plus, you have this random walk. Okay, given me eta plus, I have this collection of independent random variables, which is, if eta is random, we assume that this collection is also random, is also independent from eta. Okay, eta could be random. And so we have this random walk. So this random walk is associated to this profile here. Okay, every time I go right, I have an minus exponential with parameter rho. Every time I go down, I have exponential with parameter. So, okay. And I do the similar construction to the minus side of eta. Okay? But now I'm reversing the orientation here, in the sense that I keep the same orientation, but I just reverse the sign. Every time I go down, I will sum minus exponential with 1 minus rho. Every time I go right, I have exponential with parameter rho. Okay? So I have these two random walks. And so let's denote the competition interface. So I will denote this path here. Of course, this is a dual. It's a path that lives in the dual, but it doesn't matter. I can, just, this is the starting point is 0, 0, is a dual, and then so on. I will just parameterize the competition interface according to each path, to each step. Okay? And the theorem says that, so in this regime here, there exists almost surely a limit direction, or a limit slope. I'm just dividing the second coordinate by the first coordinate. Actually, the first part of the theorem it holds even if you don't have this case here. But I'm more interested in that case here. And so this limit exists almost surely. And we can actually compute the distribution of the limit by using this formula here, which says that the probability that the competition interface, that the slope of the competition interface is smaller than a, that is, that the competition interface is to the left of the line with direction a, is equal to the probability that the maximum of this random walk here, the Sn minus rho, is bigger than the maximum of the random walk Sn plus rho a.
And the A depends?
Yeah, so the dependence is that rho of a is 1 plus square root of a to the power minus. It's the same that appears with the Boltzmann function that we have seen before. Okay, it's the same way that we map the direction of the slope of the Boltzmann function with respect to the invariant measure. And so first, notice that we are always assuming that these collections are all independent. Okay, So these two random walks are independent as well. Because this one just depends on the positive part of eta, that one just depends on the negative part, so they are independent. So sometimes we can actually have a very explicit formulas for this maximum. I'm sorry, it's my... I forgot to turn off the... Okay, so in some case we can actually compute the distribution of this maximum and distribution of this maximum, and then they are independent, so we just compute the probability that one of the variable is bigger than or equal than the other variable, which are independent variables. So it's a very, most of the case, not in most of the case, but...
This holds for deterministic eta.
Yeah. This holds for deterministic eta or for random eta, where it's independent of the environment that you were constructing the last passage times. Okay? So the theorem says that, so we have this competition interface here, and we know how to compute this asymptotic direction by using this formula. Okay? Okay, I will show you some examples where we can actually. So, for instance, we will see that if you start with a Bernoulli type of initial curve, okay, let's say you go up in eta plus, sorry, go down with probability p plus, and you go left with probability 1 minus p plus, and then you do the same in eta minus. So you have like what we call a Bernoulli type of initial. It's a random walk type with different intensities, with different probabilities. Then we can actually compute this using standard results for random walks. And we have a very explicit formula for this. And we can also compute this in the periodic case, also when you have periodic type of profile. Okay, I will show you the computations later. Not really the computations, but the results, because this is just textbook computations. Okay, so there are some key ingredients in the proof of this theorem. And the first one is this localization lemma. So let me erase this.
And does this change a lot if you suddenly decide to move your zero?
Sorry?
If you suddenly decide to move your zero, this doesn't...
Oh, if I decide to move it downwards?
No, along the edge curve.
Along what? I don't know.
Along the curve.
Along the curve.
Oh, if I decide to move it along the curve.
Yeah, so you will have
Another competition interface, yes.
another competition interface, and the slopes will be probably
Will be the same.
will be the same.
Yeah. No, this slope will be the same, but the distribution, I mean, the distribution will also change. It might change.
Because the eta is different.
Yeah.
Like a different eta. And so suppose it was like this, and then you start here, you get a different type.
Yeah, because so the heuristic says that somehow the direction that the competition interface will choose will be very affected by what happens in the beginning.
Okay.
It's like this is also telling you, you will see that this random walks, they both have a negative drift, so this maximum is well defined. They start at 0, they have some negative drift, so the distribution of the maximum is actually related to what happens in the beginning, because afterwards they will go to minus infinite. Okay, so if you change it here, then you will really affect what happened at the end. Yeah. Okay. So this localization lemma is very important too in the proof. And so let me do a picture here. It says that the argmax, so I will denote it the arg of eta plus or minus of x is the location. It's exactly somehow the location of the root of the geodesic. Okay? So it's the position. So remember that you can write L of eta to x as the maximum over all x along eta of L of x to of. Okay, let me just rewrite it. So we have this formula L of eta of x. You can just write it as the maximum over OZ in eta of L from z to x. Okay? So this arg here is exactly, it's not exactly because I'm writing this as the k in z. So it's the index of the location of the maximization problem. Okay? So this lemma is saying that so you have these two critical reactions here. And it says that if you, so for instance, I have my minus here. So if, and I have minus here. So if I have a which is here, for instance, which is, for instance, smaller than mu minus, and then I look to the location here. Where is the location of the starting point of the geodesic? Then along this direction here, so this location will stabilize around 0. So there exists an M, which might be random. It's random. So almost surely such that for all x bigger than 0, so the argmax will always be in an interval 0 minus, 0 and plus, and the same holds for mu minus. Okay? So actually here I'm looking at the last passage from eta plus or eta minus. Okay, so just to do the distinction. So the L from eta to x is just the maximum from L from eta to eta plus or L eta eta minus. Okay, I'm just distinguished between. So I take the maximum from here to here and the maximum from here to there. And then I just look at the locations where they happen. And the theorem says that if you go along this direction, then you have this mu minus and m plus. Also, if I see the location here, this is also going to be in this finite interval, random interval. Okay? So I will not go to the proof of this this lemma, although this is crucial. It's somehow very very technical, and I will use this to prove what we want to. Okay. But the idea is it reminds what Eric was doing in the last lecture, where you use the delta straightness of the geodesics to control this location here, and then you see that it will stabilize, because these two directions here, they correspond to, when you look to the limit shape, it's exactly the region where you have a convex set. So you use this convexity to control this location, because that's what I'm actually doing there. Okay. Okay. So first, I will prove that the competition interface should be actually in between these two critical directions. Okay, with probability 1. Okay. So the claim is that the lim is bigger or equal to mu plus, and the lim sup is smaller or equal to Okay? So here, this phi eta x is the intersection between the competition interface and yeah, so let me do some other picture here. So I have this competition interface here, correspond to this path, and so I'm looking at so x is fixed actually. So this is the other way around. So x is fixed, and I'm looking at this location here. Okay. This is my phi. Eta x. And what we want to prove is this. Okay. If you take the slope, then this will be bigger than mu plus. And if you take the lim sup, this is smaller than the mu minus. Okay. Okay. So what I'm going to do is to choose an A first, which is smaller than mu plus. And then I will prove that eventually the competition interface will be to the right of the line with slope A. Okay? That will imply that the limit is bigger than mu plus. So for that, I will first do the following. So by lemma 1, okay? By lemma 2, this localization lemma. So I can choose an M, which might be random, okay, such that the last passage time from eta minus to xa, so I'm sorry, so it's good to keep in mind that xa is xax, okay? So this is a location in Z2, and this is given by this curve with this line with slope A, okay? And the idea is to do this, and then I will send x to plus infinity afterwards, okay? So by lemma 2, almost surely I can find an M such that the last passage time from eta minus to xa is smaller than the last passage time from minus 0 to xa, for all x bigger than 0. So why this is true? So you can see this in this picture, although it's a very small picture. So I know that, you know, along this direction here, A, so it's bigger than M plus, okay? It's to the right of M plus. Sorry, no, this is not the right picture, so let me do, this is not, I want to take it smaller than, so let me do this here. So this is, let's say this is M plus, and this is A, okay, this is right. So, so M minus is here. So now A is smaller than, so if A is smaller than M plus, so it's certainly smaller than M minus. So we call that lemma 2. So if A is smaller than M minus, then the argmax will also stabilize. So if I take now along this direction here, and I look at the location of the argmax coming from eta minus, so this will be bounded. So if it's bounded for all x, so this is my xa, so I can, for instance, choose a point like here, such that the last passage time from this point to xa is certainly bigger than the last passage time from any point here to A, just because it's to the left of this point here. Okay? So now I fix this M. I know it does exist by lemma 2. And now I will also pick a parameter P smaller than P plus such that 1 minus P is bigger than rho A. Okay? And I can do this because, you know, by assumption is A is smaller than mu plus. Okay, so you have that rho A is always bigger than 1 minus P plus. Okay? So I'll choose this p, smaller than p plus. And I will define, so this is eta. So notice that what I'm trying to do here is the following, because the competition interface here, so the way I know if it's to the right or to the left of some asymptotic of some line here is by looking at what is the color of this point here. Okay? So remember that this is red and this is blue. So if the color of this point is blue, then certainly the competition interface is to the left of this point. Okay? And vice versa. So what I want to do is to compare. So it is blue if L eta plus is bigger than L of eta minus. No, because then the geodesy comes from here, not from there. And it's red if the other thing happens. So if L eta minus is bigger than L eta plus. So what I want to do is to compare L eta minus and L eta plus. So first I get I get a control on L eta minus by upper bounding this by this L from minus m to x. And now I want to do the same with the L eta plus, sorry. Okay? And for that I will use this auxiliary parameter p. Okay, so I will pick this p such that it's 1 minus p is smaller than rho of a. And I have this lambda p here. And so I will define a new half profile, which I call eta bar, okay, by taking this mu plus, here should be lambda p, not me p, okay? This should be minus lambda pk. So what I'm doing here is I'm taking another profile which would be slightly, above eta plus. Asymptotically. Okay? Of course, I'm just doing the asymptotic picture, the microscopic picture. Okay? And now, so I will look at the Boltzmann function from minus m0 to eta k, okay? Eta bar k. And I claim that this Boltzmann function should be positive for all k bigger than k0. There exists a k0 such that this Boltzmann function will be always positive for k bigger than k0. And why this is true? So this is true because I know the distribution of the Boltzmann function. So I would just need to use some sort of law of large number. So I have this point here, minus m0. And then I have a point here. So this is 0, this is k. And then I have my point eta bar k. So here it's minus lambda p k by the definition. So the Boltzmann function from this point to that point, I can just write is that the Boltzmann function from this point to that point plus the Boltzmann function from this point to that point. Okay? So the Boltzmann function enjoys this additive property. So the Boltzmann function from x to y equals to the Boltzmann function from x to z plus the Boltzmann function from z to y. I just sum and subtract this part here. And so the Boltzmann function from here to there, I know the distribution, because we compute it. And its asymptotic value is given by k plus k times 1 minus 1 over rho a. Okay? And on the other hand, when I compute the Boltzmann function from here to there, so I also know what it is, because it's just a sum of independent random variables. So I know that asymptotically in k, this will just be, so here I have the lambda p, So it will be asymptotically, so lambda p, sorry, times 1 minus rho a. Okay, and then by the way I choose p, this is bigger than 1 over minus 1 over 1 minus p plus mu p divided by p, which equals to 0. Okay? So I have this asymptotic value in k, and this is positive. So there exists a k such that this will be positive for all k bigger than k0, just using law of large numbers somehow. Okay? Okay, so I will pick this k, k0, such that for all k bigger than k0, this is positive. And now I'm almost done with the first part of the proof. So why? So I will now compare the L eta plus of xa with the L of eta minus of xa. So first I will claim that, so L of eta plus xa will be bigger than L of zxa. So why this is true? So again, use the Boltzmann function here. So I will now choose a z in eta plus such that z is smaller than eta bar k for some k bigger than k0. I can do this because the way I choose eta bar is that it should be a little bit above eta plus. And so if z is smaller or equal than eta, so I will choose z in eta plus smaller or equal than eta bar k for some k bigger than k0. So this will imply that the Boltzmann function from minus m0 to z is bigger than the Boltzmann function from minus m0 to eta bar k. And since k is bigger than k0, this is positive. Okay? And if the Boltzmann function is positive, so recall that this is, you can see this as the limit as x goes to infinity of L from z to xa minus L from minus m0 to xa. Okay? So if this is positive, then for large enough x, this guy will be bigger than that guy. Okay? So this guy will be bigger than that guy. And of course, the last passage time from eta plus to xa is bigger than the last passage time from z to xa, because the last passage time from eta plus to a is just the maximum over all possible z's. And by construction, this z belongs to eta plus. So this is just trivial. This is just the Boltzmann function. And this was also by construction. We choose the m in such a way that this will be bigger than L from eta minus to xa. So since this holds for all x big enough, this is actually saying that the big competition interface will be to the right of the line with slope 1a. Because the point, here I'm saying that the point xa will be painted blue. So the competition interface is to the right of that point. And so this limit will be bigger than, so since we choose a arbitrary, so a is just a small, strictly smaller than n plus, this actually implies that the limit should be to the right of n plus. Okay? And the proof for the other inequality is just the same we did. Just adapt the same argument to the other side of the initial profile. Okay? So one important observation here is that, so for this proof, I didn't really use that mu plus is strictly smaller than mu minus. Okay? So this actually holds also if mu plus equals to mu minus. Okay? I could do the same argument. And so this argument is also showing that if the slopes are the same, then the competition interface has an asymptotic direction, almost surely. And this asymptotic direction is given by this mu, which is the p divided by 1 minus p squared.
It's given by what again?
So the mu,
So we are in the case
yeah, so mu, so remember that mu plus is the,
equal to
so plus or minus is this, square, okay? So what I'm saying is that if p plus is equals to p minus, which means that this eta has the same slope in the plus and the minus, then what I just tell you, what I just told you is, so this implies that if p plus equals to p minus, then this argument shows that the competition interface has a asymptotic direction with probability 1, and this asymptotic direction is deterministic, and it's given by this slope here. Just because you can do the proof, and just the lim inf equals to lim sup equals to mu. Okay, just a remark.
okay. So
Okay.
P plus and P yeah, okay.
If p plus equals to p minus, this argument shows actually that the competition interface has an asymptotic direction, which is deterministic and given by this value here.
Now we haven't proven that there is absolute direction for the...
No, not yet. Not yet. No. I'm just remarking that this argument is enough to show the asymptotic result, almost surely, and to tell you what is the direction it will follow. Okay, if you start with a flat, let's say flat, not with a wedge, then you have an asymptotic direction which is given as a function of, of the slope of your initial profile. So somehow this will correspond to the characteristics of the associated Hamilton-Jacobi equation that you have for this growth process. Okay? And yeah, so let me continue with the proof. So we have this, and now we want to prove that. So now I'm assuming that p minus is smaller than p plus. Okay, and so I will do another picture here, because now I'm going to use the delta straightness of geodesics to show that the competition interface has an asymptotic direction, almost surely. Okay? So let me try to convince you with a picture. So we know already that the competition interface will be, the slope of the competition interface should be in this interval. Okay, so it will be eventually in this interval. So here, so this is the region that we are interested in. And so let's assume that the competition interface has no asymptotic direction, almost surely. Okay? So in that case, what will happen? So if the competition interface has no asymptotic direction, so it will have to wander like that. So we will be able to find two numbers like A1 and A2. Such that this kind of picture will happen with positive probability. So you will see the competition interface going to the left of the line with slope, let's say A2, and to the right of the line with slope A1 infinitely many times. Okay? So, but what is the problem with this picture? So the problem with this picture is the following. So notice that this A1 and A2, so this is A2 and this is A1. So they are in the they are in the Rarefaction region, okay, which is this. So by lemma 2, I know, for instance, if I take the geodesic from here to eta, I know that this geodesic, so it's to the right of the competition interface, so the geodesic from here to eta will end up at this side of the initial curve. So it will have to do something like this. Okay? And similarly, so the competition interface from here to there will have to do something like this. Okay?
You said lemma 2 because this is bounded interval.
Yeah, so the next step is that I know that following these A1 and A2 directions, I can control these intervals here. I know that it will stay bounded by some numbers. And so you can see here in this picture that, so this cone has a positive angle, a strictly positive angle. And you will see that the geodesic is doing something very weird, which contradicts the delta straightness. Because you know that for large enough points, the geodesic will be controlled by this cone, this delta straightened cone. So if it does this kind of movement infinitely many often, it will contradict the delta straightness property of the geodesics. Okay? So you see that, for instance, here you have some point here, and then you see that the geodesic will have to be like here, in a cone, in a very thin cone around that point. And you see that this does not happen if one is like that. Okay? So we can deduce now the almost surely convergence as a consequence of the delta straightness of the geodesics. Yeah? Okay, so let's go. So this is just to remind you, Eric talked about this, what it means to be delta straightness. Okay, so now let's go to the limiting distribution. And so the starting point to understand the limit distribution of the competition interface is this observation that we have done already, that the competition interface is to the left of AX if L eta minus of XA is bigger than L eta plus of XA. Okay, just to remind you the picture that we have. So I have this X. So here is my competition. So the location of the competition interface in the intersection of this line. So this is smaller than AX. So I have the competition interface here. So if the color of the point XA, so if it's smaller, then this has to come from eta minus. So to be smaller than that means that L eta minus is bigger than L eta plus. Okay? So now what I'm going to do, so we know that this guy is just the maximum over all possible, so L eta minus of XA minus or plus, I can always write this as a maximum over all K. So it will be smaller than 0, or bigger or smaller than 0, depending on if it's minus or if it's plus or minus, of L eta K to XA. Okay? And then I just sum I just subtract the same thing on both sides of the inequality. Okay? So L eta minus of XA bigger than L eta plus of XA is just the same as the maximum over k smaller than 0 of L eta k to xa minus L from 0.
There should be an eta minus there.
Where?
In the slide it says L eta minus from 0 to xa. It's a bit double. It's just the L from 0 to xa.
Yeah, here it's just, yeah, there's no eta minus here and there.
No,
No, there's no eta minus here and there. It's a mistake. It's a typo. Because this is a point-to-point. As soon as I write the maximum here,
right.
then the eta disappear. Okay, so it should be eta k from xa, eta k from 0 to xa, bigger than this, bigger than the maximum over k bigger than 0 of L eta k xa minus L 0 x. Okay? And that's what I call the delta. Yeah, I should not put a eta there too. This is.
Try to change notation.
Yeah. It's not the problem when we do just copy and paste, and sometimes we forgot to get rid of some older notation. And but okay, anyway, I hope you were. And delta L of x, y, and 0. So somehow that should I should keep a k here. Because this delta depends on k somehow. There is some dependence on eta. That's one point, but depends on k more than on eta itself. That's just the position at k. So now we are almost done because we know that when x is large, so this difference goes to the Boltzmann function. Okay, we just need an argument to say that, okay, we have the maximum here, so this maximum should stabilize. So if I can show that this maximum is going to stabilize, then I can use convergence for each compact interval to the Boltzmann function and then extend the convergence to the whole setting. Okay, but we have it already because we know that by lemma 2, this maximum here will be, there will be some m, such that this maximum will be actually equal to the maximum over k from minus n to 0, and the same for eta plus. Because again, I'm taking a between minus m plus and m minus. So I can use lemma 2 again to have this property that the maximum, the location of the maximum will stabilize close to 0 again. And then for each k here, I know that this path here is going to the Boltzmann function in direction a. So what I get finally is this. For each fixed m, I know that this is converging to the Boltzmann function. This is the maximum of the Boltzmann function from m to 0, from minus m to 0, and then here from 0 to m. And then I can just extend this to the competition interface. To deduce that the probability that so how do I call it? So we know already that this limit exists almost surely. Okay, so the probability that this guy is smaller than a will be equal to the probability that
This is the Boltzmann function from 0 to eta k.
This is the Boltzmann function from 0 to eta k. Yeah. So let me, I didn't wrote this notation here, so Thank you, Eric, for reminding me this. So it's this beta A plus eta k. This will be the Bismarck function. So just be sure it's from 0 to 0, 0 to eta k.
And also the plus is not, doesn't mean anything.
No, the plus means something because I'm taking the convergence. This plus here means something because I have the Bismarck function. When I look at the Bismarck function going upwards, and I have the Bismarck function going downwards. So remember, so to compute the distribution of the Bismarck function, we need first to look the Bismarck function downwards and characterize this as the invariant, the unique family of invariant measures for the LPP fluid system. But to relate the competition interface with the Bismarck function, then we use the B plus, because we are looking at the asymptotically and upwards, not downwards. Okay? And so I have this, so it's plus. Yeah, so this is always. And so remark that we can use this. So the Bismarck function has this additive property again, and I can just write it as a sum of the Bismarck function, of the increments of the Bismarck function. Okay? And then I'm done because I know the distribution of the increments. I know that they are independent and they have this distribution given by exponentials. Depending, if I go down, then it has a sign. If I go right, then it has another sign, and it depends also on the parameter. But so I just write this as a. So let me just finish what I wrote here. So it will be the maximum over k smaller than 0 of b a plus eta k to be bigger than the maximum for k equals 0 of b a plus eta. And then I just write the Bismarck function as a sum of the increments, and then use the theorem 2 that gives me what are the distribution of the increments. I know these are independent random variables and with exponential distribution, depending on where the parameter depends on where I go down or where I go right. Okay? And that's it. There's no more to do. Okay? So this is the remark I did during the proof, that when you have the flat case, then we have convergence almost surely to a deterministic direction, which is given by p divided by 1 minus p to the square. Okay? And so we can use this formula. So another remark is that, so here in this theorem here, I have a very explicit formula for, in terms of a random walk. Okay, so we know that I construct this random walk because I knew already what would be the limit related to the Bismarck function. So I construct it already knowing that I would get the Bismarck function. So somehow we believe that so some theorem saying that like this probability should be equal to the probability that the maximum of the Bismarck of the increments of the sum of the increments of the Bismarck function here to be bigger than the maximum of the sum of the increments of the Bismarck function there. This relation should be general. I think. Should hold on every last passage model where you can construct Bismarck functions. Okay? This should be general. But for each model, then you should be able to compute what is the distribution of Bismarck function. That's not really an easy task. So just in a few models we can do it. In last passage on lattice, we can do this for exponential, and we can also do for geometrical weights. In the Hamsley model, we can also, Hamsley model with weights, we can also do it when the weights are all equals to 1. But we will see that there is a very similar relation there too. And so just show you some examples where we can actually compute using classical results for maximum of random walks. So for instance, if you have this Bernoulli initial profile, where you go, we have this parameter of the Bernoulli, so P p plus is the probability that you go right, or no, sorry, that you go down, and 1 minus p plus is the probability that you go right, and the same for p minus, but going the other direction. So then it's a classical result that the maximum of, yeah, you are just some geometrical quantities of exponentials. So you know that this is another exponential. So then you can use sum of, you're just computing the maximum of sum of sine, you have sine exponentials, not really only exponentials, because you have this negative drift. So, but you can compute what is the distribution of the maximum, it gives again you an exponential. And the same for eta plus. And then it's very easy to compute what is the probability that this exponential is bigger than that exponential, and you just have this formula.
This is also the classical result, right?
Yeah. So this is this result. This is the classical result that was proved by Pablo Ferrari and Claude Kipnis in '95, where they were actually not studying competition interface, but second-class particles in the rarefaction regime. Because all this that I'm telling you is related to the totally asymmetric simple exclusion process. And there is a way, there's a one-to-one map between what we're doing here and questions involving second-class particles. So second-class particle corresponds to competition interface. And that's what I did together with Pablo later. And we were able first to compute the asymptotic direction of the competition interface using their results in the task set context. But then me and Eric, we realized that we could do this in a much more general meanings that you could, because the work of Pablo and Claude were really restricted to Bernoulli type of initial condition in the totally asymmetric exclusion process, because they use this hydrodynamic machinery to prove this formula. And so later we were able to realize that the competition interface will connect to the Busemann functions, and then as soon as we have the distribution of the Busemann function, then we were able to actually do some more general computations than what they did. Okay, so for the periodic initial profile with parameter k plus and k minus, so we can also do the same, but the formula is a little bit more complicated. Okay, so it's again using just all this machinery related to queuing theory and random walks.
What's periodic?
Yeah, so let me explain you. So let me see if I remember well. So I have one. So the k plus is so this is the eta plus. Okay, so k plus is so I go down one step, and then I go right k plus steps. Okay, and then I go down one step, and then I go right k plus steps. Okay, and I keep doing this. And there I do the similar, just exchanging things. So I go one step to the left, and then k minus steps up. Okay, and keep doing this. So this is k minus. Okay, so in that case, we also get a exponential, but where the parameter will depend on the solution of this polynomial. So remember that rho depends on A, so lambda will depend on A as well. This is for fixed rho, we have a solution, lambda plus. So since rho depends on A, lambda plus will depend on A, and on k plus, of course. So we have this characterization using maximum of random walks, and then we could just compute again. So what the probability is that this exponential is bigger than that exponential. So it's just this. So just take the parameters. It's just a combination of the parameters. It's the sum of this and divide by. No, just one divided by the sum of the parameters. Okay. And this was unknown at the time. Okay. So to finish, I think I still have like 10 minutes, 15 minutes. So let me, so we can actually use similar ideas to deal also with this geodesic forest. So just remember that, so how do I construct this geodesic forest? I did a similar procedure, but now I just, have different colors for the roots, and then I just paint the geodesics according to the initial point of the geodesic. Okay, so for instance, the geodesic from this point to eta will end up at this point, and so this point is red, so I will call it the geodesic red. And I keep doing this.
In this model, are you assuming that you have an infinite number of colors, or would you have a finite number?
I could have a finite number, I could have an infinite number. Just depend. So the colors corresponds to this kind of corner of the initial profile. Okay? Because these are the corners where you have the initial point of geodesics. So geodesic will never start here, because you can always start here and get that point and then go on. Okay, so if you want to maximize, you always have to start at the corners. So I have this forest of trees, of geodesic trees, and I want to know, so for instance, if I have a direction A, okay, a slope A, I want to know what is the probability that the corresponding color is red? Or in other words, what is the probability that the red tree conquers the direction A? You can imagine that there's some sort of competition here, but then you have infinitely many colors, and they are trying to, conquer as much as they can. Okay. In the previous guy,
They can disappear.
they can disappear. For instance, here, the orange one disappeared because it got caught by the yellow and the brown one. Okay. It can disappear, but it can also percolate. But it depends on the geometry of the initial profile. So I studied this model together with Sergio, and we were able to use similar ideas and somehow answer this question of what is the probability that this guy will conquer direction A. And so here I just described the way you color things here. And again, so theorem 2 is the theorem where I described the distribution of the Boltzmann function. I have this very precise description of the distribution of the Boltzmann function. And this theorem will also allow us to actually show, to answer some questions related to this geodesic forest. Questions like, what is the probability that this red tree conquers direction A? Okay, so let me just formalize that. So key of A is the argmax. So I'm just looking at the index where I maximize this here it should be not S but the Boltzmann function. Okay, so let me explain. So key of A is the location of the maximum in direction A. So for instance, suppose I have a line here with some slope A, and then I will see what is the location of the root that corresponds to this direction A. Okay? So again, I'm taking A. I know that in this rarefaction regime, this root is well defined because I know that it will stabilize around 0. So it will be somewhere there, close to 0. And so I'm asking the question, so what is the probability that k of A equals 0? So k of A equals 0 in this picture means that, so in direction A, the root was this one, the red one. Because this is the 0, the k equals 0. Okay? So of course this depends on the direction I'm choosing. And so the theorem says that we can actually compute what is the probability that the red tree will conquer direction A, and this will just be given by the probability that the maximum, the product of the maximum of the probability that the maximum of S minus equals 0, and the probability that the maximum equals 0 as well. Okay?
And can you calculate the probability that it doesn't percolate as well? The red one?
Oh, it's just 1 minus, no, that's a harder question. That's a harder question. I can compute as a probability that is not, that does not conquer direction A, of course, it's just there. But if you want just to ask the question of what is the probability that it just percolates, then we can get lower bounds. Of course, just if it conquers direction A, then it will percolate. You can maximize, and then you can get some lower bounds for that probability. But somehow this is a harder, much harder question to answer. And of course, actually, we.
Similar to how wide the tree is.
Yes, of course, yeah.
So why these random walks they can never go above?
Yeah, because they have negative drifts. They have negative. So for instance, here, so in this picture, I'm assuming that, for instance, the 0 here. So I have this type of corner here. Okay, at 0. So if
start with it, step down.
you step down, yeah, in the Boltzmann function.
You're always going down, so it's
Yeah, I'm fix this 0 here and say, okay, suppose that here I have this type of corner. So when you associate,
It's still true if it's not that.
but then it's random.
Zero.
Yeah, it might be random.
No, what I mean is that if there wouldn't be a corner, then also in your formula it will just
Yeah,
be
then the
zero.
first step would be positive, so the probability that the maximum is 0 is 0. Yeah, that's true. But just suppose that you have this corner here. Then if you sum the Boltzmann function according to that direction, you'll see that the first step is negative. And the same here. So if you have this kind of corner, then you have a positive probability that the maximum will stay always below 0. So it starts at 0, but then it remains below 0 for the whole time. And then again, you can use classical theory for maximum of random walks to compute this probability. So for instance, for Bernoulli initial profile, we get this formula.
Which is unknown.
What?
This is unknown.
This was unknown. Yeah.
Because this says something about the second of
No. You know, this geodesic force, I saw it for the first time in the work of this guy from Israel. I forgot his name, but he was doing this for the first passage, and of course it's much harder to deal with. Yeah. So that's Antonovich and Prokacia. Yeah. Antonovich, I think, is a Czech guy. Prokacia is from Israel. And so they were asking questions. So what is the probability that the tree at 0 will percolate? This kind of thing. Or if you start with the flat case, so they were able to prove that with probability no tree will percolate. This kind of. But then I realized that in the last passage we could have more.
So there's no link to like several second-class particles or something like
There is a link, I think, with this process introduced by Omar Angel and his co-authors. There is this, I forgot the name, but you have like several second-class particles.
Several, the second, third, fourth.
Yes, and then you have this speed task. I forgot the name, but it is related to that. I think with their machinery, then you are able to answer questions like, does it percolate or not? We can actually do this in a very specific case, but if you have, for instance, just three corners, and then you ask, what is the probability that the middle one will percolate? That you can do. It's related to the work of David Coupier. But in general, it gets very complicated formulas using their machinery. So very complicated polynomials, and it's not clear if you can really get some precise or some explicit results for this kind of question. Okay, so then, so again, we have these formulas for the profiles where you can do computations for the associated random walk. Okay, and just to finish, so in the flat case, so we have that almost surely all trees are finite. Okay, and So now, what kind of question